Greetings to the participants and organizers of Information and Control Systems Technologies Conference. Let me start my topic about intelligent information technology for inventory and utilization of construction and demolition waste from damaged infrastructure facilities. The study represents researchers from Odesa Polytechnic National University, including me, Alexey Ivanov, and Olena Arsirii and Bieliaiev Natalija, and a researcher from BA School of Business and Finance from Riga, Latvia, Natalija Cudecka-Purina. In the current geopolitical situation in Ukraine, large-scale reconstruction of damaged infrastructure facilities, including those destroyed by the war, is of vital importance. This undoubtedly requires high expenditures of domestic and investment primary resources. Under the influence of these factors, the development of intelligent IT for the inventory and utilization of construction and demolition waste is very important to enhance the efficiency of reconstructing damaged infrastructure facilities based on the use of secondary resources. The objectives that were performed to achieve this aim are shown in the slide. So we can highlight tasks that can be solved by intelligent IT for inventory and utilization of construction demolition waste. It includes initial classification of waste reception centers based on the attribute data, geospatial data, and creating corresponding database for waste reception centers, things. Automated inventory of construction waste based on comparative analysis of infrastructure objects images before and after destruction, including classification of building material types and the approximate volume estimation using large language models, LLM. Creating of a corresponding knowledge base for damaged infrastructure objects, sources, and development of an interactive sync sources map and determination of an efficient route for construction and demolition waste movement. These stages can be shown in a conceptual scheme of intelligent IT, which is presented on the slide. So let's study the method for automated inventory of construction and demolition waste from damaged infrastructure objects using LLM to analyze images. So this proposed method consists of the following stages. On stage 1, we obtain images of infrastructure object before and after damage destruction. Images can be obtained from drones, satellites, archival and private sources, as well as BIM modeled results. For further analysis, the use of visual pairs before-after damage is recommended because it allows the localization of damaged areas and identification of new objects in the scene. On the second stage, we conduct image analysis for waste classification. Specialized machine vision tools of their integration are used to perform image segmentation. The main substages on this stage include image preprocessing, image segmentation, clustering into objects fragments, and classification of the segmented objects. The next stage, waste volume estimation, is a key stage for practical application. After classifying materials in each regions of interest of the image, considering its scale, pixel areas are converted into real world areas. And the last stage is the application of LLM as a multi-instrument for explanation generation and to get report about the values of these construction demolition wastes. So successful execution of all these four stages based on comparative analysis of infrastructure objects images before and after destruction, and it depends on effective generation of prompts for the LLM. The generated prompt must have clear instructions, description of input and output data, units of measurements for the data, and indication of the level of detail for the result, as is LLM's persona role. The full text of prompt is given in the paper, and here is shown test images of the school before and after damage that were used to conduct our study. So we used LLM Gemini and other versions, but the inventory report was obtained in table form from Gemini Artificial Intelligence LLM. This table is shown on the slide. It contains description of construction demolition waste, its estimated volume, and the confidence of model that it is right. Also, the full JSON file of the report is available in the link below on this slide as this table, and the estimated volume of construction demolition waste for such four-story building of school is approximately 3,700 4,300 cubic meters. The next was a GIS version for construction demolished waste inventory was developed. Our system includes 4 modules. 3 were crafted by our team, specifically the front-end, server, and database. And the 4th module integrates queries to OpenStreetMap. System architecture and technologies. The server-side component was engineered using the Java programming language on JDK, including Spring Framework, Spring Boot, and Spring Data GPA. For the database management system, Postgres was selected, and the front-end interface was conducted using Timeleaf, HTML5, CSS3, and JavaScript. The full description of the technology is given in the source below. It's an article in Heralds of Advanced Information Technology. So in the current versions, in the current iteration, this applied IT aims to assist users in managing construction demolition waste by compiling list of relevant waste collection centers. These centers, categorized by type, are identified based on their proximity to the construction site and their capacity to accept at least one of waste types indicated by the user in the input form. Users can specify the geographical location of the construction site on the interactive map. To optimize waste utilization logistics, the system applies maximum allowable distance thresholds for different types of waste collection facilities relative to the construction site. For waste collection centers, it's 5 km, recycling centers 10 kilometers, and landfills within 20 kilometers radius. The Chebyshev distance metric was employed for distance calculations to enhance computational efficiency. And the marker symbology on the interactive map is as follows. Green marker denotes construction, reconstruction, demolition site of damaged buildings, etc. Blue marker represents waste processing recycling center. Red marker indicates landfill designated for waste utilization. And orange marker signifies a general waste collection center. So to sum up, among the advantages of this research is the utilization of advanced technologies, including AI LLMs, that enable preliminary approximate assessment of the types and volumes of construction demolition waste from destroyed infrastructure objects. The proposed method, based on comparative analysis before and after images of damage using LLMs, demonstrates significant potential for the rapid and effective classification of materials and estimation of waste volumes. The developed IT system not only contributes to more effective application of BD in the post-war restoration of Ukraine, but has real potential of becoming a universal tool for overcoming crises of a similar nature or originating from various natural disasters in different parts of the world. However, the limitations of this study include its preliminary nature, representing first approximation of IT implementation. It does not account for full diversity and complexity of construction demolition waste classification or all possible utilization scenarios. The current work also does not incorporate transportation costs to relevant centers, which could render certain waste utilization types economically unfeasible. So future research directions involve more detailed investigation of construction demolition waste with relevant experts from the construction industry and environmental specialists to refine the developed IT and improve its quality. Also expanding the database for LLM trading and for supplementing data on existing and new collection points of construction demolition waste. So that's all. Thank you for attention. All questions I accept, and certainly, and your recommendations. Thank you for your attention.